Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Dr. Anne Bouillard. She'll be speaking on guaranteed performance analysis of networks with bandwidth sharing schedulers. Dr. Anne is a researcher at Huawei Technologies, France, since 2020. Before that, she was a research engineer at Nokia Bell Labs, France from 2017 to 19, and associate professor at ENS Kazan, Brittany location, and ENS in Paris from 2006 to 2017. She received her PhD from École Normale Supérieure de Lyon in 2005. Her main research interests are discrete event systems, performance evaluation, and probabilities, including network calculus. She is the co-author of a recent book on this topic. Before I move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Finally, we request the audience to keep your microphone silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box when relay your questions. Over to you, Dr. Anne.
Okay, so thank you for the invitation, and I will speak about guaranteed performance analysis of networks with bandwidth sharing schedulers. So this is a joint work with Hossein Tabatabai and Jean-Yves Le Boudec from EPFL. So the main motivation for this work is time-sensitive networks. When you have a network where you want to satisfy some timing constraints of the transmission of packets from one end system to the other end system to ensure the correct behavior of the whole system. So such examples can be found in embedded systems like avionic or spacecraft, or also in industrial automation and campus network with the development of the 5G networks. So my objective here is to compute performance guarantees upper bound. That is that I want to compute a bound, for example, on the delay of the end-to-end delay of a packet that transit through the network. So we will speak about upper bounds of worst-case delays. And I'm mainly using the theory of network calculus. So this is a theory that has been developed in the 90s by René Cruz and then popularized by C.S. Young and Jean-Yves Le Boudec through two books from the year 2000. And you can see this as a filtering theory in the min plus algebra. So I will try in this talk to avoid too much formalism about min plus, but this is the theory it's based on. So the motivation for network calculus originally was to have a theory that is able to compute delay bounds of systems, but based on a more general hypothesis than usually the Markovian hypothesis of the classical queuing networks. But when you want to compute the performances on the internet, maybe you don't need that strict formalism to compute that upper bound, because if you have some packet loss in an internet communication, it's not such a big deal. But then new applications came for network calculus, and it was more about embedded systems like in aircrafts or network on chips, where the guaranteeing having strong guarantees on the end-to-end delays is desirable property. So there have been extensions of this network calculus to stochastic networks, but in this talk I will remain in the deterministic or non-probabilistic setting. So if you want to compare network calculus with other models, you can see it as an intermediate between the scheduling analysis, or that is also sometimes called the response time analysis or real-time analysis, and the queuing theory. So in the scheduling analysis, you have a very precise description of what happens in the system at the job level, so at every packet. And so you can have a very precise analysis that can be very costly also to compute. And it's really complex then to generalize it to large networks. In queuing theory, you have a more probabilistic analysis, but often based on Markovian assumptions, and maybe you cannot model that many scheduling policies. So network calculus is a theory that can do both modeling quite precisely some scheduling policies, but also with this theory, we can compute performances in complex networks. So if just to describe in a very broad way what network calculus is doing, is that it is a model for what is happening in the system. So you have first the input traffic, so what is transiting through the network, and we will model it through what is called an arrival curve. It models like how much data can arrive in every interval of time. And then you have also the network element, so how data is transmitted from one router to the other. And we call this abstraction the service curve, and it tells, how much traffic can be transferred per unit of time from one input, from the input of a router to its output. And then we will use some min plus operator or algorithm to combine these arrival curves and service curves and compute upper bounds on the delay or the backlog of the system. And in Huawei, we are interested in industrial networks. So this is an example of an industrial topology with like 8 switches and nearly 1,000 flows. And you have different classes of flows. You have some flows that are critical, so they really need to be transmitted from their origin to their destination in a very small time, like less than 1 millisecond. And you have other types of traffic, for example, the multimedia flows, where you have not so strict delay requirement. It can be, for example, 10 milliseconds or 50 milliseconds. And then you have the best effort. So the kind of traffic that maybe if they miss their deadline, it's not so important, but you still need to guarantee some service that are available for them. So the characteristic of this network is that it is multi-class. So they share some bandwidths and their service is differentiated because, of course, you want to give more priority to the critical flows than to the best effort. And also, you might have complex topology. So, for example, something that was some years ago kind of hard to analyze, especially in network calculus, was the cyclic dependencies. Because you have flows circulating through the network, and they could create loop dependencies and making the analysis more complex. And very few works used to deal with those kind of networks. So how will we analyze complex topologies with network calculus? So if we have a multi-class network, so each element of the network admits several classes of traffic. And the first step to analyze is to define for each of these servers what is the service, so what you can guarantee for each of these classes. And once you can do this, in fact, you can separate the whole network into one network per class, and then analyze it as, so here, 3 FIFO networks. And then we have methods to analyze FIFO networks. So what we have seen recently is that when you compute the guarantees per class, then you have interdependencies, because the guarantee of, for example, the blue class will depend on the amount of traffic that can arrive from the other classes. So it creates some interdependency, and then you need to deal with that to improve the performance. So in this talk, I will talk about the scheduling that is bandwidth sharing, and in particular, the DRR, deficit round-robin scheduling, and analyze for large networks. Okay, so first I will define a little more precisely the network calculus framework. Then I will explain how to model the bandwidth sharing policies for one server. And once we have done this, we can use these results for the analysis of the FIFO networks and then combine everything together. So let me start with the network calculus framework. So here you have a system, and so a very simple system with one flow of data entering and one flow of data exiting this system. And we work on what we call cumulative arrival processes. So in fact, here, this is a function A, and A of t represents the amount of data that arrived in the network, in the system, until time t. So because you cumulate with time, then this function is non-decreasing. And you have the same for the departure. So the d of t is the amount of data that departed the system until time t. So you assume that you have no creation and no loss of data in the system, and whatever departs must have arrived before. So the function a is larger than the function d. And so let us see how it works on a simple example. So here you assume that the system serves exactly sorry for the typo, r bits of data per time unit. So if you consider 2 times here s and t, where the system is not empty, so here you can see that the system is not empty between s and t, because you have strictly more data that have arrived than what has departed at any time in this time interval. So if you serve exactly r bits of data per unit of time, then the difference d of t minus d of s, which is what departed in the time interval st, is r times t minus s. And there is a special time when you can, so when s is the smallest time before t, where the system is not empty. So here, in fact, it's the largest time when the system is empty. Let's say it's better to say it like this. So here, it means that d of s equals a of s. So you can write this equality. So you have a relation between the arrival process and the departure process. And you can, if you take any other time, and now want to compare the difference d of t minus a of s, so if you take a time that is smaller than this special value of s, then you have only an inequality. So what departed at time t minus what arrived is less than r times t minus s. And the same holds when you take a time s that is larger than the smallest time, when you have equality between a and d. So you have this equality always, and you also have equality somewhere. So it means that the departure process is equal to the infimum when you take all possible s between time 0 and t of what arrive at time s, and 1 what can be served between time s and t. So this is what is called the mean plus convolution, and this is why network calculus is based on the mean plus convolution. Okay. So if you want to have more general services and the whole network calculus framework, so we have what we call like arrival curves and service curves. So the arrival curves is here to model what can arrive at maximum during any time interval. And we said that the arrival process A is constrained by the function alpha if for all s and t, what arrives during the time interval st is less than alpha of t minus s. So the usual type of function alpha is an affine function. When you have the value at 0 represents the burst, it is in a way the maximum amount of data that can arrive simultaneously. And the slope here is called the arrival rate, is the maximum rate at which the data can arrive. And so the process A that would be constrained by alpha must remain below alpha. And if you draw alpha from any point of A, the rest of A need also to stay below what you draw, the alpha function that you draw. The second element is the service curve. So here I will use a slightly different version, which is called the strict service curve. We say that a network element guarantees the service curve, the strict service curve beta, if we know that the system is not empty between time s and t, it can guarantee to serve beta of t minus s data. So it's kind of the reverse of the arrival curve, but it is a lower bound of what can be served by the system, provided that it's not empty during the time interval that we consider. So this is an example of a trajectory, so example of A and D, that would satisfy the arrival curve alpha and service curve beta. And what is nice with network calculus is that you can compute performance bounds directly from the arrival and service curve. Because usually you don't know exactly what are A and D. You don't necessarily know exactly, how data are served and what is the exact arrival process. But if you are able to find bounds curves alpha and beta, you can compute the arrival, the maximum backlog, that is the maximum amount of data there is in the system at each time, and the maximum delay, so the amount of time data needs to be served after it's arrived. And it can be read very easily on this drawing, because the delay bound will be the horizontal distance between the two curves alpha and beta, and the backlog, so the amount of data, will be the vertical distance between alpha and beta. So now I will explain how to analyze some scheduling policies with network calculus, and take the example of bandwidth sharing policy. So bandwidth sharing policy are policies where you share the bandwidth of network elements among all classes of traffic. So the ideal bandwidth sharing policy is called the generalized processor sharing. So you associate to each class a share of the bandwidth that is reserved for that class, and you share that way all the bandwidths. But of course, so this is kind of a fluid model of what arrives, but of course the flows of data are processed in the network through they are packetized. So there are packets in the system that cannot be that are served entirely one after the other. So you need some implementation of this processor sharing, and the easiest way to do this is to use the round robin scheduling policies. So in the round robin policy, so each class can serve one packet, in rounds. So one class after the other, class 1, class 2, etc., and back to class 1 after the nth class. But you can have more elaborated policies. So, for example, the weighted round robin. When you serve in each round WI packet for class I. So there are different ways of doing this, because in a global round, when you serve WI packets per class, you can choose to serve all of them in one batch, or to balance them among this all round. And another policy that is quite important is the deficit round robin, because it is sharing, instead of sharing the packets like in the round robin policies, when you serve packets one after the other, you base the sharing on the quantity of data. And it can be more fair, especially if packets can have different sizes. So, and now I will explain this. No, sorry. Okay, and I will explain this at the next slide. But now, what is the network calculus objective when we have this type of bandwidth sharing policies? So we have the arrival processes here for each class. And you have a global server here that offers a service curve globally to all the classes. And then you have the departure process of all the classes. But you want to find one guarantee per class. So what you want to find, in fact, is a beta I, so a service curve for class I, such that beta I is a strict service curve for class I. So in a way, you want to divide this server into n servers with an individual service curve for each class. Okay, so I will first focus on the DRR sharing policy. So here you want to have an algorithm that shares the bandwidth quite equally, not equally, but in exact proportion for each class. So to each class, you will associate a quantum. So this represents the amount of data that can be served at each round for class C. And instead of describing the algorithm, I will just do a small example here. So first, you want to serve class A. So the quantum, represents the quantum. So in the beginning, you associate, so these are the deficit counter, and they are first initialized with the quantum. So there is enough quantum to serve the first packet. And after the service, so you decrease by the amount of data that have been served this deficit counter, and you have enough also to serve packet 2, so you serve it. Now there is a third packet, but you don't have enough deficit, so you will start serving class 2, the next class. So you increment its deficit by its quantum. Now you can serve packet 1. And after the service, in fact, you had more deficit at the length of the packet, but then you don't have a second packet. So you just decrease the deficit to 0 and start serving the third class. And similarly, you increase the deficit, you can serve the first packet. You don't have enough deficit to serve the second packet. Then you go back to class 1, increase by the quantum. Then you have maybe a new packet that arrived, and here you can serve the two of them, etc. So that way you can serve all the packets. And what you can also notice is that the deficit counter is always positive, because if you don't have enough deficit to serve a packet, you will not transmit. And it is also less than the quantum that you add at the beginning of the round, plus the packet length, because you might have some deficit that was remaining from the previous round if you didn't have enough deficit to serve the next packet. And now, if you want to find a service curve that models DRR, you notice that in what I described, that if, so let's say that you can serve R units of data per time unit, you have intervals of time when you don't serve any data for the class that you are interested in, because other classes are served. But when data is served, it receives the total service rate of this network element. So you have a service curve that can have this shape. Sometimes this is too complex after to do further computation, so we also like to have some approximation. And what we like also in network analysis is working with linear approximations. So here you can find two types of linear approximations, so the green and the blue, and the maximum of the two is also a service curve. So you can also notice that this green one was the first in the literature to be defined as a service curve for DRR in the network calculus. And you see that the share of the bandwidth that you can guarantee for a class is the quantum of this class divided by the sum of all the quantums. So this gives the proportion that is reserved to the class C. And because you serve packets and then there are moments where you have to wait before serving data, you have a small constant here that is due to this scheduling algorithm. This curve is valid independently of the traffic that transits through the network element. But sometimes, when you have a flow or a class that doesn't use all its bandwidths, then the part that is not used can be shared by the other classes of traffic. So, and this can make a huge difference when you compute the delay bounds. So now we want to have more precise service curves that would take into account the arrival curves of the other classes of traffic. So for this, we can define what I call the perfect bandwidth sharing policy. It means that so as I said previously, you want to have some proportion of the bandwidth that is reserved for each class. And this proportion is phi I for class I and phi j for class j. And you said that you can ensure this proportion of the bandwidth if you have this relation between the departure processes. This tells that if between time s and t there are data of class I in the system, you know that you guarantee a service for class I that is more than this quantity that depends on what has been served for another class of traffic. And you can show that you guarantee this amount of traffic of service for class I. So how do you read this formula? So you consider class M that doesn't contain your class of interest here. You want to compute the service for class I. You take a subset of the other classes. And first, so you can compute what service is not used by the classes that are in M. And this is beta, so the global service that is offered to the all network elements, so to all classes, minus the maximum traffic that can arrive for these classes of traffic in M. And there is also another constant that is for the scheduling and the fact that you have packets and not a fluid policy. So this is what is reserved for the classes that are not in M, in the classes in M. And then here you compute the share of the class, so the proportion that is guaranteed to class I among the classes that are not in M. So among the other classes. So and then, so this is this way of doing is valid for all set M that doesn't contain the class that you are interested in. So you can take the supremum of this. So here, for example, if you had the first guarantee, so this one that was computed without taking into account the traffic of the other classes. So as in the previous slide, now taking this other traffic other traffic of the other classes, you can improve and find a larger service curve, and then you will be able to compute smaller delay.
One question.
Okay, yeah.
What does this Hij represent?
Okay, Hij represents the fact that you serve packets and not the way you are sharing the bandwidth is not fluid. So if you have something like fluid, like or bit per bit, let's say, you wouldn't have this Hij. Because you would guarantee like to have for example, if you have two classes and they both have 1/2 and 1/2, you would guarantee that you have R divided by 2 per time unit for each class. But if you take like for example here the round robin, you would say I will first serve a packet of class 1, then a packet of class 2. So here, this would represent the amount of data you need to serve the packet of the other classes, and this is what represents the constant H.
Okay, thanks.
Okay. Are there any other questions? Okay, no. Okay, so now I will talk about the WRR policy. So here you cannot really share as perfectly the bandwidth. So of course we had this constant H, but we could provide like guarantee a certain proportion of data of service that can be reserved for one flow. So here let's consider this example. So you have a class A that can serve WI packets at each round, and these packets have lengths that are comprises in between like L min, Li min, and Li max. So if you want to compute the guarantee for class I, you would say that okay, I need the minimum amount of service this class can receive within one round is at least Wi, so the number of packets that are served, times the minimum packet length that can be served. So because you know that all packets have lengths more than this one. But now, if you, in one round, look at what is the amount of data that have been served globally, so also by the other classes of traffic, in the worst case, from the point of view of class I, the other classes served packets with the maximum length. So you see here that it can start to be very pessimistic, and also that you also could be maybe lucky, and instead of receiving only the minimum amount of service, you could have served only packets with the maximum size, and your competing classes, you would have served like small packets. So the proportion here is not that well defined, and the share of the bandwidth is in between these two extremes. And sometimes it's not enough to compute finite performance bounds, even if you know that the system is stable. So the way of dealing with this issue is to slightly change the previous bandwidth sharing policy definition, and now it is imperfect, saying that instead of having the phi, we had the phi j before on the phi I, you need to differentiate with a phi j max and the phi j min. So the phi I min, sorry. So here the phi I min represent that the fact that you serve in the worst case the minimum packets, and the phi j max that the other classes will serve the maximum packet, the packet with maximum length. And using this definition, you can compute guarantees for the weighted round-robin policies. So you can do the same reasoning as previously. So to compute a service curve, you first look at the minimum proportion of the service that is guaranteed for the class you are interested in. And you still have this constant that is due to the packetization. But then you might have stability issues. In particular, if the packet lengths are very different, then you might have that the proportion you are guaranteed is smaller than the arrival rate of your data, even if you know that globally the system would be stable because the sum of the arrival rates of all classes would be less than the service rate. So you need to solve this issue, and the way of doing it is to notice that anyway, if you know that the system is globally stable because what arrives on the long run is less than what can be served, you know that the backlog in your system will always be finite and you can bound it. So here, these 2 points are just similar to what I explained before. So this one is that if you know a guarantee for some classes in M, then you can see what's the proportion that you can guarantee for the class I. And this one is if you want to compute the guarantee for classes that are not in M, then you just remove from the global service what can arrive for the other classes, for the classes in M. But then you have a constant, so that is now different from H. So it depends on the packetization, of course, but you have to take into account the backlog of the system. And the third point here is to show that, in fact, this constant, if you can compute it globally for the system, it will be finite. So you know that this constant is finite, and then you can compute finite performance bounds. So this is just a small numerical evaluation. So the red here is, so you have 4 classes of traffic and a variability between the minimum packet length and the maximum packet length. So if the load of the system is high, if you don't take into account the characteristic of the classes or the arrival curves, then you cannot compute finite bounds when the load of the server is more than 40%. So the load of the server is the ratio between what arrives, the arrival rate in the server to the server divided by the service rate. And so there were some state of the art here that didn't take into account the third point, like how to use the fact that you know a priori that the system is stable, and they would not be so they wouldn't be able to compute finite bound for like more than 80% server load. But so with this new method, you can compute finite bounds, and it is also less sensitive. So these new bounds are less sensitive to the packet length ratio. That is the ratio between the maximum packet length and the minimum packet length. So you see that you can bound the delay quite efficiently, whether with other methods it would grow to infinity as the packet length ratio would grow. Okay, so this is it for the bandwidth sharing policies. And now, as I said, the second step to the analysis of complex system is analyzing FIFO networks. So we have we can use the DRR analysis or the bandwidth sharing analysis to compute one service curve for each class of traffic, and then we obtain one FIFO network per class of traffic. So in network calculus, you have different ways to compute performance bounds in FIFO networks. So the classical one is what I call the modular analysis. So you analyze the network node by node, So there are different methods that exist, in particular the total flow analysis that I will explain in the next slide. The advantage is that you can have fast computations, but the bounds that are computed are often not accurate, and especially when you have networks with cyclic dependencies, it may lead to infinite bounds, whereas the network is stable. Now there is a global analysis on which I worked a lot these past years, and it analyzes the network as a global system. And in particular, you can have methods based on the linear programming. So the advantage is that it can improve the accuracy, especially in cyclic network when you can find really much better delay bounds, but it has a larger computation time. So you may not use it for very large network, but still for the one we were interested in, it was really possible to compute performance bounds within minutes. So I will focus on total flow analysis and the linear programming. So the total flow analysis. So this is a method where you analyze network elements one by one. And because you have a FIFO policy, if you have several flows, of course, of the same class joining at the same network element, if you aggregate them, the delay bound of the aggregate will be the worst case delay bound will be the same as the worst case delay bound for each flow, because you just serve every data in its arrival order. And let's say that you have this very simple arrival curve that are linear. So how do you compute? You want to compute the delay bound within one server. So you compute the sum of the arrival curve because they represent the arrival curves for the aggregation of the traffic. And also you can also improve this arrival curve using what we call the shaping. So the shaping represents the fact that if your data come from a previous server, the service rate of that server is not infinite. There is a link speed. So for example, 1 gigabit per second. And then you know that all the data here will not arrive simultaneously, but will be kind of regulated. So in fact, the arrival curve in the system can be improved to be the minimum of this shaping curve and the arrival curve. Now, using the DRR on bandwidth sharing analysis, you can compute a service curve. So it can be either this linear approximation or using the packet, the more precise one. And from this, you use this result from network calculus that says that a worst case delay bound is the horizontal distance between the arrival curve and the service curve, and you have your delay. And then when you want to compute the delay bound for the next server, you have to compute the characteristics of the arrival curve at this next server. Because when you have data that is processed through a network element, you may increase the burstiness of the processes. And the burstiness is increased by adding the delay times the arrival rate. So then you know what are the characteristics at the output of these servers that can be served as a characteristic at the next server, and so on. So when you have a feed-forward network, so no cyclic dependencies, you can first sort all the network elements in the topological order, and then compute the delay bounds for each server, one after the other, in this topological order. And then the end-to-end delay of the flow will be the sum of the delays on the path of the flow. And when you have cyclic dependencies, in fact, you consider these delays as variables, and you use it, and you compute a fixed point using all the relations you can compute between the arrivals and the service curves and the delays. You compute a fixed point on the delays, and this gives you the delays per node, and then you can do the same to compute the end-to-end delays as the sum of the delays per node on the path of the flow. So now this may not be very precise, and there is a way to greatly improve the performance bounds. It is using linear programming. And if you want to have bounds that can be computed in a reasonable time, you need to have some polynomial size linear program. So the main idea behind these linear programming things is that you will introduce variables, so of the form a, I, j of t, d, I, j of t, that represent the arrival and departure process at some times t at some point in the network. So if you consider the network element j, this will represent something, a process at the entrance of the network element, and this at the departure of this network element. And there will be a few interesting times at which the processes will be interesting. And this is where you will define these variables. And now the network calculus will be used to construct the linear constraints of the problem. Because, for example, if you start at the entrance of the network, between two times, you know that what can arrive, so here between time t prime and t, is less than the alpha I of t minus t prime. So here I use the linear arrival curve, but you can write these types of linear constraints. And similar for the service, you know that at some point you will have a relation between the arrival and the departures. You can also write like the constraints to enforce the fact that the system is FIFO. You know that the arrival processes need to be non-decreasing, and you need to have some causality, etc. But you can write everything that are arrival or service curve constraints as linear constraints. So usually it will give you way too much constraints, but you can use a method that I will not describe here to have a trade-off between the accuracy of the bounds and the tractability by replacing some of the service curve constraints by the delays that you can use with the previous method. And then the objective, you need to write the objective of the linear program, and it will be maximizing the surround time of a bit of data in the system. So maximizing the difference between some dates in the variable that you have written.
So what is LJ here?
Sorry, I didn't get the question. The sound was
so
pretty
this service constraints at the server. The right hand side of the inequality, there is RJ T prime minus LJ. This LJ, what is this LJ here?
Oh, okay. Yeah, sorry, I didn't really explain. I will represent a flow, and J will represent a server, a network element. So here you, okay. So J here, and the 0 here will represent what arrive in the system at the entrance of the system. So this will represent the arrival process, so the one where you know the arrival curve. And here, this represents, so you sum on all flows that crosses server J, and this represents the departure process from server J at some time, at time t, and this arrival process arriving at server J, and it's the sum of I, so the all flows that cross server J. And here J this represents the service curve of the network element J.
Okay.
Okay. And then only for so one of the drawbacks of this linear programming approach is that, we need to have linear constraints. So basically, you can have like this linear arrival curve or something on this shape, or a maximum of this shape, but you cannot take into account like this version, like this version of the service curve, for example. So we generalized this linear programming approach to take into account the first service round of, for example, the DRR policy, because some classes that have high priority may always finish to serve all their backlog within their first round. So you see here the difference between the delay if I take the red curve or here the blue curve can be huge. So it will be very interesting to improve the linear programming approach, taking into account this first part of the non-convex service curve. And to do this, we introduce some binary variable. It's called the big M technique in linear programming. And depending on whether B is 0 of 1, and you take M, a constant that is large enough, like either this some of the constraint will be dumb. So for example, here you want to enforce that in the first round you have this service. So if B is 0, it means that you must be below, so the amount of data must be below Q. But if B is 1, so this will be this will be a negative value, and this will be a very large value. So only this variable, this constraint will be dumped and useless to the program. So this is why we can have like a case disjunction in the linear programming. And so now I go to the last part. So now we want to put everything together and have the analysis of the whole DRR network using like the two parts I explained. So the state of the art was using TFA analysis only, so the modular analysis only. And so in the agnostic analysis, where you don't know the traffic, you don't take into account the traffic of the other classes, then you compute very simply the service curve per class and analyze each class independently. If you have a feed-forward network, you can do a little more. You can sort the nodes in the topological order and compute one after one using the traffic of the other classes that you can compute after each traffic class. So you have an iterative way of doing it, and you propagate everything, but there is no cyclic dependency, so it's very easy to do. But when you have cyclic dependencies, and if you want to use this linear programming approach, it's not so simple. So we have an approach that is based on an iterative scheme. So we use the state-of-the-art approach for an initial phase that will give us some preliminary bounds, and then we will use a parallel algorithm that's using a shared memory, and we can improve all the bounds, the delay bounds, the per class service iteratively as we improve the other elements. And so I think for the sake of time, I will not elaborate more on this. And finally, we will use the linear programming approach with taking into account, introducing some integer variables to take into account the classes that finish their service within one round. And we can show that this way of doing, whenever we stop the algorithm after the initial phase, will be valid. So on the experimental results, so we have we can show that we divide by 3 the delay bounds that were found by the TFA analysis. And here the different colors, in fact, show the different improvements we have with introducing more and more new techniques that I described. And more importantly, sometimes the TFA analysis cannot compute finite bounds for some classes of traffic, whereas our new method can compute quite low bounds. Okay, so this is the end of my talk. So I presented like a network calculus service curve model for bandwidth sharing policies and an iterative scheme to improve the way the delays can be computed within a DRR network. And in the same, we presented some improvement for the linear programming techniques. So the future work, and for me, it is something that is missing in the network calculus analysis, is that we never compare our bounds with simulations. So first, because simulations, like the way it is done usually with ergodic processes or queuing theory, random processes, is not very adapted because we are interested in the worst cases. So the synchronization that can happen in the worst case will happen basically with probability 0 when you do some, randomized simulation. So I think this is something that may become also kind of important if you want to assess the efficiency of our bounds, because we are able to show, okay, we improve greatly the bounds, but how much room is left for improvement also. And I thank you for your attention.
Thank you, Dr. Ren, for this informative talk. If there are any questions, we can take them now.
One question. Yes. So, does network calculus approach help you model bursty token bucket kind of traffic allocation?
It is based, in fact, on the token bucket. Like I say, like this. Let me go back to the for example here, like this. Shape of service is usually called the token bucket function, in fact. And this is really the modeling of a token bucket. Like if you have an arrival process that is not constrained and you shape it or you regulate it through a token bucket, then this token bucket will be an arrival curve for the process.
Okay, thank you.
Are there any questions? If there are no more questions, you can end this session now. Thank you and have a great evening.
Yeah, thank you.